The Netflix matrix. 100 million ratings and a prediction problem worth $1 million. This is why an entire generation knows about something called the singular value decomposition and eigenvalues. What are the singular values of this matrix? Good, but that last number is a little blurry. Hey, Julia.
Yes, David.
Enhance. Let me introduce JenericArpack.jl. This is an almost drop-in replacement for the symmetric eigensolver in Arpack, written in pure Julia. It works for the built-in floating point types, as well as extended precision types, such as the DoubleFloats and multi-floats package. To do this, it uses a self-contained generic BLAS and Lapack for all the calls that it needs. It's multi-thread safe, and it's often, for float 64s, floating point equal to the results from Arpack library calls. Because it turned out to be easy in Julia, we added a complex Hermitian eigenvalue solver that builds on top of the symmetric solver. This allowed us to implement a complex valued SVD as well. Some of you might be wondering what Arpack is and why it matters. I'm going to let Wikipedia explain what Arpack is. Julia has actually featured Arpack for over a decade. Why is Arpack so commonly used in technical computing software? It turns out that one of the great strengths of Arpack is that it doesn't need to know anything about how you store your matrix. It uses what's called a reverse communication interface. So here's an example loop on how Arpack works. It uses this reference pointer called iDo, where you call this function SAUPD, symmetric Arnoldi update is what that stands for. It updates a bunch of data structures. And then when this returns, if the value of iDo is 1, that means that you should compute a matrix vector product. Alternatively, if the value of iDo comes back as 99, that means Arpack is done. And there's a whole host of other cases. But you can see this loop implemented in all sorts of different technical computing packages. And the key point about all of this is that the actual Julia functions here, that is the matrix vector multiplication, it's completely independent of the library. So here we just extract pointers to the memory locations and then do the matrix multiplication. Now, Arpack is a Fortran library with decades of history. What is the goal of our package here? The goal of JenericArpack is to translate Arpack from Fortran to Julia. I'll clarify a little bit what I mean by a translation in a second. But one of our big goals here is to minimize dependencies. There are all sorts of efforts out there in the Julia ecosystem doing profoundly interesting things in terms of extended precision arithmetic, generic linear algebra, and so on. I am trying to minimize all dependencies on these so that given any new machine that comes up, you might be able to use something like Arpack on it. So you might be curious about this word translation. And what I mean by that is literally a translation. So JenericArpack should do as close to the same thing as Arpack as possible when given the same inputs. Let me just explain a little bit about what I mean by that in terms of that previous Arpack loop. The vision is that you could simply retarget the symmetric Arnoldi update function to avoid the call into the Arpack.jl library, and rather instead use the call from JenericArpack, and everything else should work just the same. It's going to use the same type of reverse communication. It's going to use the same memory structures and layouts. And indeed, This is by and large what we've accomplished with just a few caveats. So this means if you're doing anything complicated with the symmetric Arpack solvers, you should be able to use generic Arpack as a drop-in replacement. One of the things people might be wondering is, why bother doing all of this? There are other packages in the Julia ecosystem, KrylovKit and Arnaldi-method.jl, that largely do the same thing. They provide a generic type of eigenvalue solver inspired by the type of Arpack. They are not trying to translate Arpack, and rather they're trying to take what we know about linear algebra and how to use Julia as best as we can and build something better. I think these are excellent ideas, and I strongly encourage people to look into these and try and improve them. That said, why did I decide to translate Arpack? The single best reason to do this is I was interested in seeing what was possible. I wanted to learn about Arpack, and I wanted to see how close we could do to translating it into Julia to make it easy to use on all sorts of new and emerging architectures. The plan to do this is just to port Arpack's Fortran code function by function. Let me give you an example of what I mean. Here is the code for a particularly simple function in Arpack. This is a Fortran code that takes in a few arrays. So it takes in the length of the array, a double precision array of length n, and then another double precision array of length n. Takes in a scalar input that gives a tolerance, and it outputs the number of converged Ritz values. So if we go down, we can look at what this function actually calls. And so it includes some debugging and setup and statistics that we'll look at in a little bit. Allocates a few variables. The code computes a tolerance, eps to the 2/3. So this is your machine tolerance eps. And then it runs through your array and checks a simple bound, and then it updates. This turns out to be a timing structure. That's it. So a couple notes about this. It's very well commented, and it has a lot of good information about what the inputs and outputs are. But the goal is just to translate this function basically verbatim into Julia. So the first thing we do is we translate the introductory documentation. We make a couple of little changes to the input-output routines. So a few things, rather than updating a output variable, which is a common convention in Fortran, we are going to return a variable instead, which is a much more common convention in Julia. The other thing is we are going to take a few structures that manipulate the debugging information and the statistics information, or rather the timing information that Arpack collects. Other than that, the two sets of documentation are by and large the same. Let's look at what the example code looks like. So here is the main body of our port of this. First thing it does is check a time. The next thing it does is it checks some array lengths just to make sure we're not going to overflow our bounds. We allocate our output, and then by and large, we run through the arrays. So a few things I want you to notice. We are going to preserve the original Arpack comments. So the way I did this is I would cut and paste all the Fortran code and just go through it line by line and translate it. So this allowed me to keep the comments in line, which are hugely informative and extremely well done. These timing macros are used to do a few things. So in Arpack, they are always updated, so Arpack is always collecting timing information. We, on the other hand, can get good meaningful timing information depending on if you want it. So if the stats variable is not nothing, then we are going to update the time associated with this. And these macros just map out to this code. So DLAMCH is a BLAS Lapack call that gets the machine epsilon in this case. So rather than doing that, we're just going to replace that with a function. There's a reason we're not going to replace it with eps of t to the 2/3 that I'll get to in a little bit. So that was one function. And at this point, things seem more or less straightforward. Doesn't seem like we're getting anything super complicated. Whenever you're porting something and you think it's going to be simple, you should always ignore those beliefs. At some point, I discovered that the Arpack code uses what are called save variables in Fortran. Save variables look like subroutine-specific state or global variables that are specific to a subroutine. If you want to learn about some of my initial investigations of these things in Julia and in terms of Arpack, please check out this blog post. Of course, if there is persistent state, then it begs the question of what actually happens when multiple threads try and use Arpack in Julia by itself. Here's a post on the Julia discourse that describes one experience with trying to use Arpack's eigcall in a multi-threaded loop. The upshot is, it crashes and does not work. This made me briefly revisit some of the assumptions about how easy I thought this was going to be. One set of Arpack state proved particularly interesting. Arpack includes calls to the Lapack random number generator. It does this to get information on how to initialize the Arnoldi process, which uses a sequence of matrix vector operations. This means that if you start Arpack and then run it again, you can get different results, even with the same inputs. This is extremely annoying behavior when you're interested in reproducing codes. The only way to reproduce this would be to essentially restart the entire Julia process to get Arpack to restart its random numbers. One fun thing I discovered as I was doing this port project is that we can actually reset Arpack's random number generators. All we have to do is the minor task of looking up the offsets to these internally stored random number states. There are a few various tools to do these. Essentially, we need to get the offsets to the variables relative to some function that we know. We look up the pointers to the function that we know, and we essentially use that to get the offsets to where the random variable states are stored in memory. And then we can reset them to the initial values that Arpack would use. So we can essentially get the same output from Arpack as the first time you would call it, even in light of its random number generator. I've got this working on Linux and the Mac. Unfortunately, on Windows, I'm not quite sure how to get them because it seems like the dynamic link libraries or the DLLs that Windows use a slightly different scheme to load code into memory using different offsets and regions. And I haven't entirely figured out how to get these. So if anyone is watching this and knows how to get those from a DLL file, please let me know. I would love to hear that. And in case you are wondering, this does indeed mean that we need to port the Lapack random number generator. Here is the code for the random number generator. It has a long sequence of constants. This maps exactly to the same random values that Arpack will give when given the same random seeds. Back to that subroutine specific state that Arpack uses. What do we do about that? We simply allocate a state structure that has subroutine specific state for all of the different subroutines that use it. How do we then use that? Well, we use a simple attach and save macros. We have a whole list of variables that need to be mapped to the subroutine state and then saved on exit. And so there's a few macros that just take this list of variables. We have one list for each subroutine that needs it, and then execute commands to extract it from the shared state. And then at the end, save it in the final outputs. Using that state allows us to continue porting the Arpack Fortran code. The remaining details that are a little tricky are the use of the goto commands in Arpack. For all of the sequences of goto commands, we were able to entirely avoid them. We have a simple while construction with a number of state flags that implements exactly the same routines. We use view liberally to mirror how Fortran treats memory and map it onto the Julia analog. And then we have lots of testing. Here is an example of the testing that we do. This is for one of the internal routines, DSAITR. That's the symmetric Arnoldi iteration update. So this is what actually updates the Arnoldi, or in this case, Lanczos factorization to the next step. This involves a whole bunch of reverse communication and other finicky state. The way we test this is we take in a problem input, we allocate duplicate copies of all intermediate data, and then we execute a sequence of commands, one targeting generic Arpack, one targeting the Arpack shared library, and we check that the results of the two are identical. We do allow the norm computations to be a single floating point number off. All of the other results should be bitwise floating point identical for float 64. One of the things that we needed to do to achieve full bitwise accuracy was to implement the OpenBLAS norm2 function inside of Julia. As the comments here say, this is tricky because the OpenBLAS version uses the 80-bit extended precision arithmetic operations that are available on x86 processors, but they are not available by default in Julia. Initially, we tried using some double-double operations to simulate extended precision. However, one of the really nice things about having that 80-bit extended precision is that you actually get an increase in the exponent range, which means it's easier to implement a floating point norm computation that achieves full 64-bit accuracy. One of the things I love best about Julia is that it allows you to mix both very high-level constructs and very low-level constructs seamlessly in the same code base. Here we take a number of ideas from the BitFloats.jl package and actually implement arithmetic operations with the 80-bit extended precision arithmetic. This allows us to implement a norm function that matches that in OpenBLAS exactly for single-threaded code. Getting the norm right was important. It turns out that the Arpack recurrence, and indeed most Arnoldi occurrences, are extremely sensitive to the precise values of the norm. Because those 80-bit extended precision registers are not available on other platforms, we use the synthetic double-double approximation instead. After writing lots of test cases to ensure that we really are getting exactly the same thing that Arpack is getting, the next step is trying to understand some of the performance implications of the code. In order to mirror the Arpack library as closely as possible, I wanted to ensure that the code was allocation-free because the underlying Fortran code is allocation-free. While I was tracking down allocations, I wrote a small little script that is illustrated here. It's called allocations.jl. And what it does is it takes the code of a file, or in this case, the current file, and produces a report on where the allocations are. I posted a note on it on the Julia discourse if you'd like more information. We will see a few illustrations of how it works. There were two problems that caused the vast majority of my allocations. The first cause of many allocations involved a construct that is used in Arpack, which we then mirrored in generic Arpack. In this case, we take a linear work array, we take a view of it, and then we reshape that view. We do this twice, and then we copy between the two. If you use that previous track allocations code, you will see that this allocates in two places. The first one we expect when we allocate the work L array. The second one we do not. When Julia executes the copyto command, it checks if the arrays that are referenced in the copy operation are unaliased, that is, they don't share any memory regions in common. These arrays do not share any memory locations in common. However, when you reshape a view, Julia can no longer infer this, and it defers back to checking whether or not they share the origin pointer, in this case work L. Because they're both views on work L, it can't be certain that they don't alias each other, and so it performs an extra copy. Fixing this seemed non-trivial, and so we simply wrote our own copyto operation to handle these cases. This one was a real head-scratcher. We saw allocations on the line while true. After much debugging, this was responsible for those allocations on while true, because the line should have been const Arpack time is equal to float 64. Without the const, Julia's compiler cannot infer that the type remains constant throughout the entire execution. If I can be permitted another brief aside, I wish there was a strict mode with no sloppiness allowed and allocations are errors. When I'm trying to port some of this Fortran code, it can be done in an allocation-free way, and any allocations I would like to know about with reference to the exact line that is causing them. I realize this can pose difficulties in terms of code generation and optimization. On the other hand, this would have saved me quite a bit of time. One of the interesting things that we were able to do was actually to avoid reverse communication in the interface. We can take in an object that will allow us to manipulate the code that would have been done with reverse communication and simply perform them exactly where they should occur. The way this works is we take in an additional state variable called IDoNow. This is a pun on Arpack's IDo variable name to refer to the fact that we are going to do it now, immediately, instead of using reverse communication for it. This maps very nicely onto Julia's concept of dispatching on objects, and we will see the performance implication soon. There are a number of uses for Hermitian eigenvalue solvers. In Arpack, these need to use the complex valued non-Hermitian interface because there is no complex valued Hermitian interface. Adding the Hermitian eigensolver was a frighteningly small number of lines of code. This took advantage of the fact that the Lanczos iteration of a Hermitian matrix gives you a real symmetric matrix, just as you get in the symmetric case. Here's the actual diff of when I got an initial version working. I needed to extend the norm call. I needed to add real valued types to some of the type specifications. And that is almost it. In very few places, I needed to just take the real part of a complex valued number whose imaginary part is 0 mathematically. In order to get some of the higher precision libraries like DoubleFloats and multifloats working, we need to execute a few small patches to add functionality that we use. If you want to use a particular package and we know how to fix it, there will be a macro that executes all of the fixes. What do these fixes accomplish? They handle things such as these. The fix is simple. We simply add the missing definitions. In this case, this is conversion from a multifloat back to an int, and also evaluating this value of eps to the 2/3. At this point, we're going to talk about performance. For a large sparse matrix, this happens to be the augmented version of the Netflix matrix. We get extremely similar timing to Arpack itself, called via Julia. If we did allow Arpack to use more threads, then it can accelerate its performance a little bit. That said, remember that most of the time in large Arpack computations is dominated by the work that you do as part of your reverse communication. So the actual implementation of Arpack tends to be a very small part of the overall computation time. We see a similar story with SVD, although it seems like the Arpack SVDS call might do with a little bit of optimization. If you want to look at a more micro benchmark of just the Arnaldi update step, you can see a slightly different story, which is that we are actually slightly slower than libarpack. I have a few closing notes on this slide. In case anyone is interested about learning more or contributing, two great small projects would be to understand where the Julia code is slower than the pure Arpack code in that micro benchmark. Another easy one would be to test some of the more exotic interfaces that have been coded but not yet tested. My vision for the future of generic Arpack is that having a well-studied industrial library like Arpack implemented in pure Julia, it makes it more accessible and approachable in all sorts of scenarios, from teaching to scientific applications. I'm super excited to see what people use it to do.